Okay, welcome back to the Chapter 15 review. Today we're going to talk a little bit about enthalpy. Enthalpy is the heat content of a system. Remember that heat is just how much energy a system has. Enthalpy is when it changes. So you're either going to have an endothermic system or you're going to have an exothermic system. In an endothermic system, you're going to be requiring energy to break the bonds rather than releasing energy. So in an endothermic system, your heat is a reactant. In an exothermic system, your heat is a product. That means that energy is released. You don't need as much energy when you get to the products right there. So there's a graphic of this in Schoology if you want to look at it side by side. Endothermic, heat is needed. Exothermic, heat is produced. Enthalpy changes for exothermic because you're producing that heat. The heat is being given away. That means your heat content for the system is negative. So you're going to have a negative delta H. And when you have a positive when you have an endothermic reaction, you're going to have a positive delta H because you're absorbing that heat and that enthalpy. So right here, when you look at this, your reactants have more enthalpy or more heat than the products. When the reactants have more enthalpy than the products do, that means you have released heat to your surroundings. Your delta H is positive. Your delta H is negative. It's less than 0. And so you've released heat to the surroundings. That's like a heat pack. When your reactants have less energy, so their enthalpy is less than the products, they have to pull heat in from the surroundings. You have a positive enthalpy, a positive delta H. And that is an endothermic reaction. You have absorbed heat. So, all of these are thermochemical equations, and a thermochemical equation is a balanced reaction that includes the physical states of the reactants and products and the energy change. That's kilojoules heat right here. This is an exothermic reaction because heat is a product. The enthalpy change of combustion is the enthalpy change for the complete burning of 1 mole of a substance. And on your thermochemistry reaction resource page, this table is listed there. So you look at the delta H of combustion anytime something is burning. And here are some formulas in case you need them. Remember that this is negative enthalpy because it's an exothermic reaction. So combustion is the reaction of a fuel with oxygen. We learned that in Chapter 9. And food is the fuel in combustion reactions inside of a biological system like our body. So right here it says how much heat is evolved when 54.0 grams of glucose is burned, according to this equation. Well, first off, let's go back here and look at delta H of combustion for glucose. We know it's combustion because it says right here that this burns. So since it burns, it's combustion. And our delta H for combustion of glucose is negative 2,808 kilojoules per mole. So the first thing I'm going to write right here is that my delta H of combustion is negative 2808 kilojoules per 1 mole. And if I've got kilojoules per mole, and right here it's got 54 grams, and it wants to know how much heat. Well, heat is measured in kilojoules. So I'm going to go from grams to moles to kilojoules. Oops, I don't know what happened there. So I'm going to set this up as a conversion, and I'm going to go from 54 grams of glucose, C6H12O6, and from grams of glucose, I'm going to go to moles of glucose. Grams goes on the bottom, and from moles of glucose, I'm going to go to kilojoules. Both moles get a 1. Kilojoules gets that 2808. You can put the negative in there. Just make sure that you don't subtract. You multiply that. And grams comes from the periodic table, and it's 180.18. So when I calculate this out, I'm going to get 54 divided by 180.18 times negative 2808. And I'm going to get negative 841.56 kilojoules. And that makes sense. It's an exothermic reaction. That's how much heat is given off. That's why it's a negative delta H. Sometimes we're going to have molar enthalpies of vaporization. This is the heat required to vaporize 1 mole of a substance. And molar enthalpy, or the heat of fusion. And this one's weird. It's melting. I don't know why it's not called molar enthalpy of melting, but it's called molar enthalpy of fusion. And it's how much heat is required to melt 1 mole of a substance. And this table is also on your reference sheet. One thing to note, vaporization, you're also going to use these values for condensation, because condensation is the opposite of vaporization. Delta H of fusion, you're going to use these for freezing and for melting. And delta H of vaporization, you would use for vaporization. Remember, those are their opposite phase changes. So right here it says, how much energy does it take to boil 45 grams of methanol at its boiling point? Energy is going to be measured in kilojoules. So I'm going to go 45 grams of methanol, and I go back and I'll look, okay, boiling, that's vaporization. So the delta H of vaporization for methanol's right here. That would be vaporization 35.2 kilojoules per mole. And I'm going to go from grams to moles, and then moles to kilojoules, 35.2 over 1 mole. And then 1 mole over grams. I'm going to go back here and look. My formula for methanol is CH3OH. So the molar mass is 32.05 that I calculated from the periodic table. So I'm going to do 45 times 35.2 divided by 32.05. And I'm going to get 49.42 kilojoules. I want you to try this third one. Since it's melting, you're going to look at the delta H of fusion for water, which is 6.01. And I believe your answer is 24.01. I want you to make sure you can set that up and get that answer. Don't worry about that one. And this right here, there is a picture in the section of Schoology that you might find useful where we kind of drew this out on the board. Thanks for your attention, and I hope that this review helped.